Given a real value x such that x is greater or equal to 0 but less than or equal to 1, show that this inequality is true. We're going to have two methods to solve this problem. The first one is using the AMGM inequality, and then the second method is somewhat of a shortcut. So let's use AMGM. We notice that the degrees of our fractions in the numerators is greater than the degree in the denominator. So when we see something like this, our first reaction is to try to use polynomial division in order to simplify the terms. So let's go ahead and rewrite each fraction. We set this division up just like how we would divide a number. So we're going to go ahead and divide. When we divide the first fraction, we are left with x minus 1, that's the quotient, plus 1, which is the remainder, over the divisor, which is x plus 1. Now let's do the same for the second term. In order to perform long division on polynomials, we have to make sure the numerator is completely expanded. So we have 1 minus 2x plus x squared. This is divided by 2 minus x. So we first start from the highest degree and then go downwards. We have negative x. This would give us x squared minus 2x. When we subtract, we have 1. So when we write out our result, it would be the quotient, which is negative x, plus the remainder over the divisor. Notice how here we have a positive x and a negative x, so those cancel out. And now all we have to do is simplify the minimum value of this. Because even though we have a negative 1 here, it's a constant, so we'll just subtract a 1 later on. We don't have to worry about it for now. Now let's apply the AMGM inequality. Here we have x plus 1 and 2 minus x on the reciprocal, but we could just use the AMGM inequality on the denominators. So if we add these two terms up and take their arithmetic mean, we would get 3 because the x's cancel out, divided by 2 is greater or equal to the geometric mean of these two binomials, x plus 1 times 2 minus x. Now let's square both sides. We have x plus 1 times 2 minus x is less than or equal to 9 over 4. Now that we've got these base binomials settled out, we can actually now focus on our original problem, which is dealing with the reciprocals of these two expressions. So 1 over x plus 1 plus 1 over 2 minus x is greater or equal to 2 times the square root of the products. Now we see that this product is showing up. Well, thankfully, we've solved for it up here. So how can we transform this? Well, when we take the reciprocal, the signs flip. And we have 4 over 9 on the right-hand side. And if we take the square root of this, we will get 2/3. And then if we multiply 2 on both sides, we get 4 over 3. Notice how we've just manipulated this inequality in order to become like this inequality. So what we're left with is 4 over 3. So our original expression, which is the sum of these two fractions, is greater or equal to 4 over 3. But remember, we have to subtract this 1 because we kept it from earlier. So in reality, our original expression, if we subtract 1 on both sides, is greater or equal to 1/3. So there we have it. We have proven that this inequality is true. I know I said earlier that we were going to have 2 methods in this video, but now we're going to have 3. So here is a second solution to solve the problem using the trivial inequality. The trivial inequality is when you have something squared is greater or equal to 0. This just means that any perfect square must be non-negative. So when we're solving this using the trivial inequality, the first step would be to always move all the terms to one side of the equation, such that we're in the form of something is greater or equal to 0. In this case, we're going to subtract -1/3 on both sides of the equation. And we're also going to eventually combine all three fractions into one big fraction, and we're going to give them a common denominator. So the common denominator would be 3 times x plus 1 times 2 minus x. Now what do we have in the numerator? Well, the first term, we would give it 3x squared times 2 minus x, plus the middle term, which is 3 times 1 minus x squared times x plus 1. And then we have to subtract the final term, which is x plus 1 times 2 minus x. This is greater or equal to 0. So let's first zoom in on the numerator for now. We're going to expand and simplify it. The first term gives us 6x squared minus 3x cubed. The second term gives us 3x cubed minus 3x squared minus 3x plus 3. And our third term gives us x squared minus x minus 2. Now we're going to add all of these terms together. So we have no x to the cubed term because they cancel out. We have a 3x squared term plus another x squared term, which is a 4x squared term, minus 4x from these two terms, plus 1. That is over the denominator, which is greater or equal to 0. Now, how can we further apply the trivial inequality? Well, in order to apply the trivial inequality, we need to make a perfect square appear. Thankfully, we can do that because this numerator becomes 2x minus 1 squared. So this perfect square must be greater or equal to 0. The denominator is still this product. So by the trivial inequality, this part is greater or equal to 0. And what about the denominator? Can it always be greater or equal to 0? Well, the answer is yes, because we know that x has a value between 0 and 1 inclusive, which means that the denominator will always be positive. Strictly positive. So if we have a non-negative number divided by a positive number, it is always going to be greater or equal to 0. It will work out. So now we have proven that the inequality is true. Why? Well, here is our reasoning. We assumed that this was true. Because we assumed this was true, we kept simplifying it, and we ended up with an inequality that was true. Because our final inequality was true, it's telling us that our original assumption was also true. So now we have proven that the original inequality is true. Now there is a final shortcut method that we're going to use, and we're going to apply something called Titu's lemma. Titu's lemma states that if you have real numbers a and b, when you have a squared over u plus b squared over v, it's always going to be greater or equal to the sum of a and b squared over the sum of u and v, where a, b are real, and u, v are positive reals. Now, how can we apply this to our problem? Well, we can let a be equal to x, b in this case is equal to 1 minus x, u is equal to x plus 1, and v is equal to 2 minus x. We don't even have to do any manipulation. We just have to substitute this in. So doing this would give us that the OG expression is greater or equal to the sum of A and B, which is 1 squared, over the sum of U and V, which is 3, which is 1 over 3. So look how fast that was. All I had to do was directly apply Titu's lemma, which is actually a special case of something called the Cauchy-Schwarz inequality. I encourage you to explore this inequality too if you're interested.